and we'll share the screen shortly. Okay, all of you can see my screen now, I believe. Okay, and the chat issue is still there. Okay, hopefully we'll be resolving it tomorrow. Okay, fine. All right, where are we? We discussed about how does this how to perform how to train the machine learning model, especially the um, linear regression algorithm, correct? And also we have seen, right, systematically, how we can fit this the linear regression model into our machine learning life cycle. To start with that, we have learned how to train a machine learning model. But before you train a machine learning model, you need to ingest the data, and then you need to perform the exploratory data analysis to understand what insights you can get it from this data. Okay, so we plotted the data in charts, and also we discussed about some statistical terms like what is data distribution. To view the data distribution of each quantitative variable, we can use histogram. We can also use box plot to interpret or to understand the distribution pattern of the quantitative variables. Okay, and then we proceeded with exploring scatter plot. Scatter plot is helpful to understand the linear or the correlation between the quantitative variables, right? Two quantitative variables, and followed by that we have seen the heat map. So heat map, in the heat map we plotted the data dot cors output. So data dot core, the core function, CORR function, that is the one gives the correlation values between the quantitative variables, between square feet and price. What is the correlation value between the bedroom and price? What is the correlation value? Okay, so that, right, it gives the correlation value, but to plot it in a chart like a heat map, so it looks nice and right to interpret the values in a pretty appealing way. We have used the heat map. So here we could see that square feet and price, got correlated very well. And I explained you between the input and output variable, the correlation should be good. Okay, if the correlation value is good, in the sense that if it is closer to one, that means both the quantitative variables are correlating very well, which means square feet and price, these two are correlating well. And the bedroom, in our example, right, bedroom and second, and the price, housing price, these two are correlating well. That is what, see, bedroom and price, these two are correlating well. Very good. We could see a very good, strong. There is a strong relationship exists between these two input variable and with the corresponding output variable price. Okay. You can also see it this way also. Okay, here, the heat map looks something like this. Someone asked this one, okay, the square feet and price, how do I see that? But here it is, you need to look at this way. Okay, in the x-axis, you just think, at the bottom, the input features mentioned. On the left side, right, vertically, they mention these columns. Okay, and ideally, you need to interpret this way. Okay, or if you see bedroom and square feet, are these two, correlating well? If you see this way, yes, bedroom and square feet, in these two are independent variable, but still it is correlating well. It is not good. See, the input feature should correlate well with your target variable. In our case, the target variable is price. Okay, the input features, right? So like the square feet and bedrooms, each independent variable or input feature should correlate well with your target variable price. But there should not be any correlation between these two. It is not correct. Okay, this is violating one of the assumptions of linear regression. If there is a correlation exists between between the independent variable itself. Look here, the square feet and bedrooms. If you see, there is a strong correlation here. Okay, this is not correct. Okay, this is called multi-collinearity, multi-collinearity, collinearity. Okay, in case of multi-collinearity, so you are not supposed to, continue with training the model. But for the sake of understanding how to fit how to train a linear regression algorithm, we just considered these two input features and then we started training the model. Correct? So, right, by ideally, there should not be any correlation between the independent variables. Instead, each independent variable should have a correlation with the dependent variable. If there is a correlation between the independent variable itself, right, then that needs to be addressed. Okay, how to address that we will see it later. So the heat map is helpful to understand which features are correlating well with my target variable. Those features are helpful. Supposing, let's bedroom is 0.35 instead of 0.95, it is 0.35. That means bedroom and price is not correlating well. Hence, I'm not supposed to use bedroom in my model. I'm not right. I'm not supposed to use this column or feature to train the machine learning model. In this case, the linear regression machine learning model. Okay, so you need to simply remove this one. Okay. But here it is correlating well with this one, but at the same time, bedroom is correlating well with square feet. Similarly, square feet, if you see 0.98, if you see this one, right, bedroom here, so in this quadrant, these two are correlating well. Okay, so there is a correlation between the independent variable itself that is against the rule. Fine. Okay, so next what we did, and we have splitted the given original data into training and test split. The default training and test split is 75-25, but here I mentioned test size equal to 0.2, which means 20% of the data I use it for testing test data set. Remaining 80% of the data, right? I use sample it, randomly. Okay, so that is for training purpose. So here I use the linear regression class and then I created an object. Using this object, right? I fitted the model, linear regression model got, trained here. And next step is we applied the trained model, the linear regression model. In our case, the trained machine learning model name is model itself, model.predict on the unseen data. This is to evaluate how well my trained machine learning model, in our case, the linear regression algorithm is, performing well in the sense how accurately it predicts. So when you apply the train model on the unseen data, in our case, which is a test data set, it gives us the predicted value. Now, you need to subtract the predicted value from your actual value to find out the error. Okay. So what I will do is I will stop, the coding part for a while. Now what we will do is, right, let's take the digression for a moment to understand the formula of the slope and intercept. This is the formula for the slope and intercept. So what is the slope formula? X minus X bar and into Y minus Y bar divided by X minus X bar whole squared. Sum of X minus X bar whole squared. So that is the formula for the slope and the intercept. So Y bar minus BI into X bar. That is the formula for this one. So what is this? Xi is for each and every value in your data set. Supposing in my data set, let's say I have the values or something. Let's in the X, right? I have input feature X. Let's assume that for the sake of simplicity, we have only one input feature called X, and then the dependent variable is Y. This is, you just think, this size. This is the price of the house. This is the square feet. Okay. For the sake of simplicity, I just use the small values here. For X, I mentioned this is your independent variable. Okay, independent variable or independent variable. This is your dependent variable. Okay, or target variable. Okay, this is input feature or independent variable. Okay, so here I just computed the mean of this one. Mean is average. Right, so this is your mean. Okay, mean is 3. If you add all the 3, right, all the 5 values, 5, sorry, here 3 plus 2, 5, 5 plus 5, 10, 14, 15, right? The total of the x values are 15. And if you take the average, how do you take the average? So add all the values divided by total number of values. So 15 divided by 5 is 3. This is called your x bar. So we got the value of x bar. So my x bar is what? Mean here, which is 3 here. Similarly, for the y value also, we need to find out the mean value, which I already computed it. So this is 3.6. What is xi? Xi is nothing but 1, 2, 3, 4, 5, each and every value. I need to subtract the mean value from each and every value. Okay, if I x minus x bar, look here, this x minus x bar. So 1 minus 3 is how much? So this is the mean, okay? This is the one we are subtracting it from here. 1 minus 3 is minus 2. So 2 minus 3 is minus 1. 3 minus 3 is 0. And 4 minus 3 is 1. And 5 minus 3 is 2. X minus x bar, we got it. Next one is y minus y bar. So y bar, we already know this is my y bar, right? So mean, we represent the notation as bar, okay? Y bar means the mean value of y. So mean value of y is 3 point. We need to subtract 3.6 from each and every value of my y. So that is what we have done it here. Okay. Why we are doing this? Because we need to plug in these values here. X minus x bar, this one, and y minus y bar. Okay. And these values, right? These two we need to multiply it divided by sum of x minus x bar whole squared. So x minus x bar, this one you need to square it. So x minus x bar whole squared. Okay, that is the one you need to do it. Okay, fine. So in this case, yeah. So by doing so, we will be able to find out the value for it. For example, if you do it, what will happen? So here, x minus x bar whole squared. What this one is going to be 4. Okay, and you need to take the square of this one, and then you need to, if you take the square, this one is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay, x minus x bar whole squared. So why do we have to square these values? Because if we are going to add all these values. If I add all these values, what will happen is the plus and minus will get subtracted. So minus 1 will get subtracted from plus 1, minus 2 will get subtracted. We don't want the values should get subtracted here. Instead, we want to square these values because I wanted to add all these values. Okay. So in this case, 8 plus 2 is 10, correct? The sum of x minus x bar is 10 and x minus x bar whole square. So what is x minus x bar? You need to multiply these two things. Minus 2 into minus 0.6. What value you will get it here? 1 second here. Somebody is calling. Just give me a minute. Now we're running. Let's go. Okay. So here, if I multiply these two things, what will happen? X minus, yeah, this is correct, right? So sum equal to 10. Equal to 10 and x minus x bar and y minus 2 into 0.6, 1.2 and negative 0.4, correct? 0 into this one is 0 and 1 into 0.4 is 0.4, correct? 1 into 0.4 is 0.4 and 2 into 1.4. How much 2 into 1.4? 2.8, correct? And then if you take a sum on this one, what you will get? You will get 4. Correct? And now we got the sum of x minus x bar whole square. This is my denominator, the denominator 10. And then x minus x bar, and y minus y bar. If you take a sum of this and we get 4. So 4 here, 0.4. This is what my slope. We have obtained the slope value. Got it? The next thing is we need to find out the intercept value. Okay, before obtaining the intercept, first you need to compute the slope value. Now we got the slope value. Next step is the intercept value. Intercept here is intercept B0 is equivalent to y bar is what is the 3.6 minus the mean of y. Okay, and bi is your slope value. Your slope is 0.4. Okay, and into your x bar. What is your x bar? X bar is 3. So how much you will get here? What is the value you will get? 3 minus 3.6. Yeah, you will get, yes, 2 point. You are going to get 2.4. Yes, you are correct. 2.4. That is the correct value. Okay. My intercept is 2.4 and slope is 0.4. So what is the equation of my linear regression? Linear regression, y is equal to intercept is 2.4 plus my slope is 3.6 into x. Correct? This is what my, well, now the x value is this one. If you if you plug in this value here, what will happen? 1 into 3.6 is 3.6 and plus 2.4. What you will get? You will get 5, is equivalent to yeah, 3, okay, 6.41, yeah, 6, right? You will get 6. That is what your predicted value, y predicted. So y predicted is 6 here. Okay, and yeah, so that is what we are getting at. That's how if you plug in each and every value. So now, 1. Next one is you try with 2 here. Okay, sorry, here, not 2.4. Yes, yes, you are correct. 0.4. That's what I was wondering. 0.4 and plus, it's not 3.6. I got confused here. 0.4 and 2.4. Yes, yes, you are correct. 2.4, right? 0.4 plus 2.4. 2.4 into 1 is 2.4 plus 0.4 is your 2.8. For this first day record, right? For this first record, the predicted value is 2.8. Okay, 2.8. Similarly, for the second record, what is the predicted value? So we know the slope and intercept. So intercept is 0.4. Sorry, not 2.4. Yes, yes, you are correct. 0.4. Okay, is this correct? No, yeah, it's 2.4 only. It's correct only. Sorry, guys. Sorry for the confusion. This is 2.4, then 2.4. Yes, yeah, 2.4. Yes, 2.8. Similarly, for the rest of the values, what is the predicted value? For the second record, y is equal to 0.4 is the intercept, that's the constant value, plus the slope is 2.4 into 2 here. The x value is 2, right? The x value is 2 here in this case. And we are going to get how much? Yes, correct. Yeah, tell me. Yeah, okay. Here we are going to get 3.2, right? 0.4 into 2 plus 2.4. Yeah, end of the day, you'll get 3.2. So, right, 3.2 for the second record, right? So, the y values, the actual value of the housing price is 4, but the predicted y values after plugging in this value, we are getting 3.2. Okay. Likewise, you need to compute the values manually. Okay, if you want to compute it manually to understand this. Okay, so that's what I plotted it here. So for this is my x. This is my x here. Visually, if you look at it here, this is my x. This is my y-axis. So here in the x-axis for 1, right? 1, the value is 1 is there, and the corresponding y value is 3. So this is 1 comma 3. Okay. So this is the one. Okay. And then second one is 2 comma 2 is to 4. 2 comma 4, right? 2 comma 4. This is 2 comma 4. And similarly, this record, if you see 3 and 2. So for the let's say, the square feet is 3, the price is 2 here. For the square feet 4, the price is 4. And for the square feet 5, the price is 5. You just think that way, okay? This is how the value will get plotted. Okay. Now we have the value for the slope and the intercept. So this is the equation. We got that equation. For the equation, right? We got the values here. So 2.4 is my intercept and 0.4 is my slope. Okay, so next what we are going to look at it. Next one is, let us understand what is residual, what is an error is all about. So we have seen the equation. First time, from the first session also, I have written the equation something like that. Beta naught plus beta 1 x plus, c, not c, e, right? E is, kind of error. So what is this error is called? Error is also called as a residual. Residual. What is residual or error? Actual value minus the predicted value. That is called your error. Error is equivalent to actual minus predicted. This is very, very important. You remember it. Okay. You need to remember this. Fine. So what do you mean by error analysis? Here, what happened? My intercept was 2.4. Okay. In this line is touching somewhere here. 2.4. When I draw the line somewhere here, this is what my predicted line. The red color one is the predicted line. It contains the predicted values. What is that green color? Green color, this ball. This is my actual value. This is my actual value. This is my actual. This is my predicted. So this line, the predicted line, right? This is called your regression line, or this is what your y equal to beta naught plus beta 1 x, or estimated value of the estimated values or the predicted values lie on this line. So this is my actual, this is my predicted. The difference between actual and predicted, right? This dotted line, this is called your my error. So here similarly, right? These two are somewhat close by actual and predicted, but still there is that the distance. So and this is called my error. I call it an E1 for each record, right? We have an error 1. So this is called error 2. The difference between actual and predicted is error 2. And for the third record, in this case what happened? It is the actual is falling way below this predicted line. So in this case, the actual is falling way above this line. Hence, it is a positive value. Since it is falling, sometimes the error will be negative also. Okay, this is E3, the actual, and this my actual, this my predicted. The difference between actual and my predicted is E3. Here also, there is a difference. This one we call the E4, and this one we call the E5. The difference between actual and predicted. So E1, E2, E3, E4, E5, these are called my error, or which is nothing but the residual. If you work with the sample data, we call this error or difference as residual. If you work with the population data and if you find out the difference between actual and predicted, that is called error. If you work with sample data, we call that as a residual, but in general, we work with the sample data only. Got it? So that is what it shows. And if you see here, next, what I did here, I just plugged in the predicted value. You remember initially I have computed the predicted value, correct? That one I just put it here. This is my x value, this is my y value. So the mean value of my x is 3 and the mean value of y is 3.6. And what is the predicted value? So how did we arrive at y is equivalent to The intercept value was 2.4 and then the slope was 0.4 into 1. So the first one is going to be what? 2.8, correct? That is what this predicted value, 2.8, right? This is the one. I put it here. Okay. And similarly, second value, for the first record, right? Record number one, record one, and second record, the predicted value is 2.4 plus 0.4 into the value is 2 here. Okay. And 2. And for this, you will get how much? 3.2, you will get it. The predicted value. Okay. And similarly, for the third record, this is my third record. Okay. This is second record, my first record. For the third record, and the 2.4 remains same. The slope also remains same. Into 3. You will get 3.6. Correct? Same way for the fourth record, fifth record, we plugged in these values. What values? 1, 2, 3, 4, 5. That's all. We know the intercept and slope. Once you get the value for the intercept and slope, where all you need to just plug in the value of your x. For in this case, we have 5 records are there. For each record, you need to plug in the x value here. Okay, this is my x, this is first record of x, second record of x, third record of, and again 4 and 5. So if you plug in 2.4 plus 0.4 into 4, 2.4 plus 0.4 into 5. So you will get 4.0, and then here you will get 4.4. Okay, that is what we can see that. So how did we get the predicted value? Since we know the intercept value and then slope value, what we did, we plugged in each and every value of my x. And when I solve this equation for each and every line, I get the predicted value. Now, okay, fine, we got the predicted value. So if we subtract the actual value, right, the predicted value, if you subtract from the actual value, that is what I said, the residual or error. So usually, right, we use the term error only. Okay, some cases they say error or residual. They use it interchangeably. Don't get confused. So actual minus predicted. This is very, very important. The difference between this is the actual. This is the actual housing price. Predicted housing price. Actual housing price 3, but I predicted it as a 3.8. What is the difference between the actual and predicted? Minus 0.6. This is what I mentioned it here. This is your error. This is called your error. Okay. This is called your error. Actual minus predicted is your error. Okay. And then what I did, I just computed the y minus y bar. Y minus y bar, 3.6 I subtracted from each and every value. I got this one and I square these values. Okay. When I square these values, I get 5.2. Why did I square this? Because I'm going to take a sum of y minus y bar whole squared. When why do I square it? Because I'm going to sum all these values. If I sum all these values, the plus and the positive and negative will get subtracted. I don't want that to happen, hence I square these values. Sum of, this is equal to 5.2 and the actual value, sorry, predicted value minus my actual value, right? So that is what this one shows here. Correct? That is what it shows. Yeah. And then next one is yp minus y whole squared. Okay. So I'm doing that one also. Y minus, okay, it's already did it, right? Y minus yp. Okay. Here, okay. There is a, okay. This is not required actually. Yeah, actually, y minus y bar whole squared. Okay, let it be there. It's not going to cause any problem. This is where actual and predicted, and actual and predicted, and then y minus y bar whole squared is fine. Okay, and my y predicted value is this one. Okay, yp minus y bar. We can see that one here. Here, there is something called R squared, guys. There is something called R squared. Okay, here the why I have used this one, right? The formula for the R, I just write it here so that there should not be any confusion. So once you train your machine learning model, you need to evaluate the model accuracy. How well my model predicts. Is there any way can I quantify the accuracy of the model? Yes, we use something called R squared. Okay. So the formula for the R squared is sum of yp minus y bar squared divided by sum of y minus y bar squared. For that reason, I put it everything here. Okay. y minus y bar, it is there. And then y minus y bar whole squared is there here. And then yp minus yp minus y bar. This is y bar, yp minus y bar, and then yp minus y bar whole squared. Okay, so this one is point yp minus y bar. Okay, yp minus y bar whole squared and y minus y bar whole squared. Everything is available readily here. If I plug in these values, what is going to happen here? Yp minus y bar whole squared is 1.6, and then here it is going to be y minus y bar whole squared. Y minus y bar whole squared is how much you will get it. If you add all these values, you will get something like this is 1.6, and sorry, y minus, it's already there, right? Yeah, y minus 5.2 or 1.6 divided by 5.2. If you divide this value, what you will get it? How much you will get it? Approximately, right? Your R squared is going to be approximately 0.02. Okay, 0.02. Your R squared is approximately 0.02. So your R squared value is supposed to be closer to 1. Any value closer to 1 is good. Okay. But when it comes to software packages, Python, you don't have to compute the R squared value manually. It gives you the R squared value automatically. Okay. You don't have to compute it manually. Okay. But you need to understand the rationale behind the R squared, how the R squared value is computed. Okay. And visually, if you look at it here, right? So this is my y-axis, this is my x-axis. Okay. And this is my yp, right? This is my yp. The predicted values are there here. And my, for example, this is my actual value, y, right? You just think no, this were y, and this is your predicted value of your y that is lying on this line. And then y bar. What is y bar? Y bar is your mean average. Correct? Average. So average is always, most of the time it will be there in the middle. Okay. So if you draw a line somewhere here, right? So in this one, the middle one is your average. And your x bar is something like this. Your x bar, the mean value of your x is somewhere 3, right? So this is the middle one. So you just remember that the mean is the middle one. In the case of the x, right, x-axis, the middle one is 3, okay, and the y-axis is somewhat 3.6, right? See, so if you draw this here line, straight line here, this is my mean of x, this is my mean of my y, okay, and here yp minus y bar, this is mean of my y, right? For this y-axis, the mean value is there in the middle. This is my y bar. So yp minus y bar, this one, if you square it, right? That is what we are doing it, divided by y minus y bar, y minus y bar. We are squaring this distance, okay? And these two we are squaring it, and these two also we are squaring it. Yp minus y bar whole squared and divided by y minus y bar. This distance we are squaring it here. Okay, visually also you can find out. So using R squared, we can measure the accuracy of the model. Any value of your R squared value is closer to 1. That means the prediction accuracy is good. Okay, so in this case, 0.02 is not good. Just for the sake of simplification, to give you a demo to help you to understand a simple way, I used a very simple number, small numbers, hence the accuracy is not that good. So if, for example, if your accuracy is 0.9, okay, which is closer to 1, that means your model accuracy is good. Any value closer to 1 is good. But still, right, you need to explore the opportunity to increase your R squared value. Okay, fine. So in the case of simple linear regression, we use the R squared as a matrix to evaluate my model's accuracy, how well my model predicts. Let's assume that my R squared value is 0.9, so which is closer to 1, hence my model accuracy is good. For example, your model accuracy is 0.6, 0.5. That means your model is not performing well. The accuracy is not good. So it requires some kind of tuning. How do you do some kind of a treatment or tuning? It requires some kind of intervention, correct? You need to include additional features. Because I've used only one feature, with that single feature, I'm getting only my R square value is 0.6 or 0.7. That means my model is not explaining well with the single input feature. It may require additional features to explain my outcome variable y, target variable y. Got it? So that is probably right. By adding additional features, your model accuracy can improve. So now that you understood the term residual is nothing but the error. What is error? The difference between actual and predicted. This is the actual value of your housing price. We are predicting the housing price, right? That is the whole objective of this exercise, right? A machine learning, the linear regression algorithm. We are training it to predict the value of the y. Okay, so you might be asking this, and already this value, sir, why should I predict it? Okay, this is my training data set. In this case, you don't have to predict it. In the case of test data set, so you test data set to be splitted, correct? 75 in our example, 80% of the data we use it for training purpose. Remaining 20% data we use it for test purpose. The 20% of the data contains both the input and output feature. Okay, x and y is there here also. But what we are doing is, when you apply the model on the test data set, we are just showing only the input feature. The model give you the estimated housing price. Okay, you just assume that, right? We applied the model on the test data set. So the test data set, I have the actual price of my, the test data set housing price is also there. Actual and predicted is also there, right? So the actual is there here. Predicted already, we got this one. By applying the model, we got the predicted value, correct? So now, this is the predicted value. The difference between actual and predicted is this one. Okay, and the formula for R squared is the predicted value of your y minus the mean of your y whole squared divided by the actual value of your y minus the mean of your y whole squared. Okay, the predicted value of housing price minus the average value of housing price whole squared. This one is your actual housing price minus the mean of your housing price whole squared. If you do this one, you will get some value that is called your R squared. With that, you can evaluate or you can justify, right, how well your model is predicting. This is a matrix. R squared is a matrix. Okay. But in the case of multiple linear regression, we use something called adjusted R squared. What will happen is when you use R squared, it will be biased. It will work only for the simple linear regression, but in the real world, most of the time you work only with multiple linear regression algorithm. So you will have more than one independent variable will be there, correct? So in that case, you cannot go by R squared. Why? Because if you use the matrix R squared, it will be biased. Simply, if you add more number of input features, the R squared value also get increased blindly. But when it comes to adjust R squared, it penalizes the features that are not adding any value to my predicted value. or prediction, or which are not helpful in terms of predicting my outcome variable. Okay, so adjusted R squared is the one penalizing the features that are not helpful in terms of my predicting value. So I just write it here so that you'll be able to understand what I'm trying to say. See, the R squared is something like this. For example, right, you are working in a project. In your project, 10 people are there, okay, including a project manager, okay? 10 people are working in a project. But let's say you are the project manager. Above you, vice president is. They are directly reporting to vice president. Okay, let's say initially you have 5 people were there in your project. Now you are saying, hey, I'm overburdened. Can you give me additional number of people in my project? Because 10 people job is done currently by 5 people. Give me 5 more people. He approves that and he gives you 10, 5 more people. So 5 plus 5, 10. Currently you have 10 people are there in your project. Now the vice president will expect the project manager to deliver it in a much faster manner, right? So whatever the task he gives, he wants you to, he wants the project manager to deliver it faster because he has given 10 people, right? Correct. So what happens is when it comes to R squared, since I know we have given from 5 to 10, it will simply increase the R squared value, blindly, like, let's, 0.70 was there for, 5 features. You just, think 5 or 10 is the number of features, like x1, x2, x3, okay? The more the number of features you add it, the R squared will get, will get inflated. 0.70 and the 0.80 it comes. Okay, but you might think, oh, this is good, man. So more the number of features, it gives me higher accuracy. 5 பேர்லேருந்து 10 பேரா கொடுத்தா எனக்கு வந்து அக்யூரேசி ரொம்ப நல்லா வருது அப்படின்னு சொன்னா கரெக்டா இருக்குமா? அவுட்புட் வந்து எங்களால சீக்கிரமா கொடுக்க முடியும். இப்போ சிம்பிள் எக்ஸாம்பிள், இப்போ இதை ப்ராஜெக்ட்லாம் பேசிக்கிட்டு யூ ஆர் கன்ஸ்ட்ரக்டிங் ஹவுஸ், ரைட்டா? ஆக்சுவலி 10 பேர் வேணும் அந்த வீடை கட்டுறதுக்கு. 5 பேர் தான் கொடுத்துருக்காங்க. 5 பேரை வச்சு அந்த வீடை வந்து 10 நாளுக்குள்ள கட்டி முடிக்கணும்னு சொல்றாங்க, முடியல. நீங்க வந்து என்ன சொல்றீங்க, ஒரு மேனேஜர் எனக்கு இன்னும் 10 இன்னும் 5 பேர் கொடுங்க சார், அப்பதான் என்னால கட்ட முடியும்னு சொல்லி சொல்றீங்க. அவர் என்ன பண்ணாரு, 10 பேரை கொடுத்துட்றாரு. 10 பேரை கொடுத்தோன்னே என்ன பண்ணும், வைஸ் பிரசிடென்ட் என்ன நினைப்பாரு, 10 பேரை கொடுத்துட்டேன்ப்பா நீ கேட்ட மாதிரி, இப்ப நீ வந்து 10 நாளை முடிச்சு கொடுன்னு கேட்பார். பட் உங்களுக்கு தெரியும், ஆஸ் எ ப்ராஜெக்ட் மேனேஜர், நம்மளுக்கு வந்து 10 பேர் தான் இருக்காங்களே தவிர, அவன் வந்து கேவ் ஒன்லி த ஹெட், he did not give பிரெயின், ரைட்டா? 5 பேர் தான் பிரெயின் இருக்கு, இது 5 பேருக்கு பிரெயினே இல்லை. அந்த மாதிரி ஆளை கொடுத்து வச்சுக்கிறோம். எப்படி வந்து 10 நாள்ல கம்ப்ளீட், யூ கிவன் மீ அடிஷனல் 5 பீப்புள், வாட் இஸ் த யூஸ்? ஓகே, பட் ஸ்கில்டு பீப்புளா கொடுத்துருந்தா 10 பீப்புள்னா 10 டேஸ்ல கம்ப்ளீட் பண்ணலாம். நீங்க வந்து ஏற்கனவே 5 பீப்புள் இருக்காங்க, இன்னும் 5 பீப்புள் கொடுத்துட்டான்னு சொல்றீங்க. பட் அந்த 5 பீப்புளும் வந்து ஸ்கில்டா இருக்கணுமே. ஸ்கில்டா இருந்தா தே ஆர் சப்போஸ் டு கான்ட்ரிபியூட். இல்லை ஸ்க்ரோல் அப் ஸ்க்ரோல் டவுன் பண்ணா என்ன யூஸ் இல்லையா? வந்துட்டு மொபைலில் வந்து இன்ஸ்டாகிராம் ரீல் பார்த்துட்டு போகிறேன், என்ன வில், ரைட்? ஸோ தெர் இஸ் நோ, ஜஸ்ட் அ சிம்பிள் அனாலஜி கைஸ், ஓகே, டோன்ட் கெட் மீ ராங், ஓகே? ஸோ ஹியர், ரைட், ஸோ ஹியர் த சேம் திங் இஸ் ஹேப்பனிங் when it comes to R squared, like how a VP thinks, hey, I gave you 10 people, so you will be thinking, okay, the R squared is good, okay, and the accuracy is good, but end of the day, R squared is not helpful as a data scientist, right? In the case of multiple linear regression. So that's when the adjusted R squared is coming into picture. What it does is it penalizes the features that are not helpful in terms of predicting the outcome variable. So 10ல வந்து எத்தனை பேர் வந்து கான்ட்ரிபியூட் பண்றாங்க, ஆக்சுவலா 10 பேர்ல வந்து நீங்க கொடுத்ததுல 8 பேர் தான் வந்து கான்ட்ரிபியூட் பண்றாங்க. மீதி 2 பேருடைய கான்ட்ரிபியூஷன் சரியில்லை, அவங்க பீனலைஸ் பண்ணிடும். அவங்க கான்ட்ரிபியூஷன் வந்து இட் டவுன் பிளே இட். பட் இது என்னன்னா ஓவர் பிளே பண்ணி காமிக்கும், இது வந்து டவுன் பிளே பண்ணி காமிக்கும். Down play na, it will penalize, those features are really, for like I said, a number of power points in my house is 20. அதனால என்ன யூஸ், with the number of power points in my house is 20 or 50, that doesn't help me to predict the housing price, right? So hence, you need to drop this feature, okay? But even if you include it, adjusted Haskell will penalize this. Hey, this feature is not helpful, I'm not going to consider him. Okay, so adjusted R square is, you'll be using it to measure the accuracy of your model. So this is one of the metrics, adjusted R square. Okay, adjusted R square, one of the metrics that we use it to measure the linear regression model accuracy. And then what we do, right, we will also use something called sum of squared errors. Sum of squared errors and total sum of squared error. And then we have something called mean squared error. So what is mean squared error? So this is what your error, isn't it? Error. This column is error. This is your actual minus predicted. That is what error. And 3 minus 2.8 is, sorry, yeah, 3 minus 2.8 negative 0. Okay, there is some problem here, right? So predicted value is the correct. Okay, predicted maybe the opposite, right? The predicted value minus actual is minus 0.6. Okay, இப்படி பண்றோம். Okay, predicted minus actual எல்லாம் ஒண்ணுதான். Okay, and then yeah, 3.2. Okay, in this case, y minus yp. There is some problem, right? Okay, let's go by this one here. Okay, so the actual minus predicted is the error. Okay, this is the error. Okay, we got the error. So you need to come. So now, instead of adding these values, right, you are going to square this value. The actual minus predicted இங்க கொடுத்திருக்கோம் பாரு correct இதுல இது square பண்ணிட்டு we are adding this value. This is called sum of squared error, right? Sum of squared error. Sum of squared error is 1.6. Predicted minus your actual whole squared அப்படின்னு சொல்லலாம் இல்லையா? Actual minus predicted whole squared பண்றதுனால வந்து மாத்தியும் போட்டுக்கலாம், ரைட்டா? So this is the sum of squared error, total error. So why we are squaring it? Because the okay, this plus and minus will not get subtracted. I want to see the total effect. If this gets subtracted, I will not able to see the total effect, total error. Hence, I square these values. See, since I don't want to get subtracted, right? So, right. So, and then if you add this one, it was sum of squared error. Instead of summing this error, sum of squared error, square பண்ணிருக்கோம் இல்லையா? This is called error. We squared the error. And if you add all the value, that is called your sum of squared error. Instead of summing this one, if I take the mean squared error, mean of in the squared error, mean is mean squared error. புரிஞ்சுதா? அவ்வளவுதான். If you take the mean of this one, that is called your mean squared error. If you add all these squared error value, that is called sum of squared error. So using some mean squared error or mean absolute error, they call the mean absolute error or mean squared error or root mean squared error. There is something called root mean squared error. So you take the mean of these values, the average of this one, and then take the square root on that. That is called your root mean squared error. So what is the root mean squared error you are getting it? Let's say my root mean squared error is 1.2. For this given set of features, I got the root mean squared as 1.2. Okay, wow. So this is another metric. So metric one is adjusted R squared. Metric 2 is RMSE, or you can use mean squared error also. Mean squared error also. Simply take the mean. But the advantage of RMS is 1.2. Now it will give you the error in the units of your predicted value. Predicted value in the 1.2 in the meaning. So it gives the root mean squared will give you the value with respect to the unit value of your y. But mean square, it will not give you the the unit value of your y. Okay, so that is not giving that. Hence, we are taking the root mean squared error of this one. Okay, so now that you understood what is residual and how to evaluate this model accuracy, we can use the metrics like adjust R square in the case of multiple linear regression. Either we can use mean squared error or root mean squared error, we can use it. Okay. Now that we are done with the theoretical part when it comes to linear regression, next we will go ahead and take a look at how we are going to calculate the R squared value. So as of now, you are clear. I will just execute this one more time so that I can give you the demo here. Exploratory data analysis, we already did that. Anyhow, it's not required. Feature engineering is not required. Okay, I just created the X and Y. I split the data into training and test data set. Next one is I'm going to train the linear regression algorithm, and then I'm going to apply the trained model on the test data. So test data, and then this is my predicted value. Okay, and then next one is the R squared value. So in this case, what I did, I applied the model on the test data set. For that, right, you need to use predict function. Okay, model.predict and x underscore test. Okay. See, remember guys, fit method and then predict method. Fit is to train the model. Predict is to apply the train model on the unseen data. If you remember these two at least, right, that will be good. Fine. In this case, what I did, I applied the trained model on the unseen data, use the predict function. Okay, fine. So now my y underscore predict contains the predicted values of the housing prices for the test data. And then what I did, right, since the test data value is very less, I just, applied the model on the training data set itself. For that, I'm using another variable, y underscore train underscore pred. Okay. So this one contains the predicted value of the training data itself. Okay. Fine. And then next, what I did, I just used something called R squared value, R2 score. You remember R2, R squared, I told you, right? Using R squared, we can measure the model accuracy. So in this case, there is a built-in method called R2 score that is available as part of sklearn.metrics. Okay, I already imported. Look here, mean absolute error, mean squared error, R2 score. Everything is available as part of the submodule called metrics, which is available in sklearn package. That is the one I have used it here. And look here, R2 score, right? It is already imported it. And for this, I'm just passing the actual value, actual housing price value, and then predicted housing value of my training data set. Because if I use test data set, the value is very less. It will not give me the good value. Okay. And then what I do, right? Use training says number of features here. Yeah, I'm computed the adjusted R square. So there is no built-in adjusted R square is available. Hence, what I do, right, I'm going to use this formula. The formula for computing the adjusted R square is 1 minus R squared into n minus 1 divided by n minus k minus 1. What is k? K is the number of features in your data set. Okay, 1 minus R squared into n minus 1. N is nothing but total number of records in your data set. Okay, and n minus 1 divided by, so your total number of records minus number of features. Okay, minus 1. That is what, right? You need to pass these values here. When you pass this, you will get adjusted R squared. So in this case, what I did, so n underscore train, okay, and that is the one contains the total number of records in my data set, and then the k underscore total number of columns in my data set. So rows and columns, total number of records, total number of columns. So basically, we need to pass some value, right? For the n underscore train, I'm going to pass it. For k, I'm going to pass k underscore train. Okay, simply if I execute this one, it gives me adjusted R squared also along with the R squared value. Okay, and then okay, I just execute this one. Look, I just executed this one, right? Correct. And then here you can see R squared value is 0.99, which is very closer to 1. But remember one thing, the adjusted R squared will always be lesser than your R squared value. Lesser than your R squared value, because the adjusted R squared is the most unbiased one. Okay, this is the one is biased one when it comes to multiple linear regression, because the adjusted R square is penalizes the features that are not helpful, or the importance of the features are not that good in terms of predicting the housing price in this case. Okay. Okay, now we can say, okay, my model like is really good. Fine. And next one is the feature importance. Look here, in this case, I have used this data frame, and we have something called model.coef. For each and every input feature, what is the coefficient value? Okay, this is the slope value for your bedroom. The slope value for the bedroom is 16,962, and for the square feet, the slope value is 163. I just write it here so that you will not get confused. Everything you learned already. Okay. Only thing is you should know what exactly here. So your y is equivalent to simply plug in this value. Okay, your square feet is okay. The intercept is not there here. We can also print intercept. Okay, the intercept is there down. Okay, now 1 second, I'll just show you here. Intercept, I printed it at the bottom, I think so. Okay. Okay, here it is there, right? I'll just put it just above this so that there should not be any. Or did I printed it here? Okay, 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 okay. I'll do one thing. I'll just put it. Look here, intercept is this one. Okay, we got the intercept value computed automatically. We did not use any manual way of calculating this. It is calculated automatically by my model. Okay, and here my intercept value is 12607 and plus my slope value for square feet is 163 into my square feet. This is the column name. Okay, so remember this is the beta 1, this is the beta naught, and plus the bedroom slope is 16962 into bedroom. For example, in your data set, the first record bedroom is 2 into 169. This is slope, guys. Okay, beta 2. Many of them, they get confused here. So along with the bedroom, the coefficient value, coefficient, when you see the term coefficient along with your feature name, that means this is the slope value for your bedroom. For the bedroom, the slope value is this one. For the square foot, this is the slope value. For each feature, there is a corresponding slope values. For square feet, this is the slope value. For the bedroom, this is slope value. If you plug in this value, you're all set, right? And again, for let's say your square feet is 100 or 1000 into 163 plus 2 into this one, and plus this you add it, you will get the predicted value for your housing price. But don't get confused with the numbers which I explained you while 1, 2, 3, 4, 5. No, here it is not 1, 2, 3, 4, 5 in the data set. It is, slightly bigger number. Okay, that's the reason why we are getting that value. We will also see that data here. Look here, square feet 1500, number of bedrooms 2, 3, and this is your housing price, right? Your housing price, if you see 300,000, 3 lakh. Okay, so for 2 bedroom, so for the bedroom 2 into 169 something like the slope you need to multiply it, and for the square feet you need to multiply that square feet related the slope, and plus the intercept value you need to add it, you will get the predicted value. That predicted value, if you subtract from the actual value, you will get the error. Is it clear or not? Intercept, we got the intercept value beta naught, and beta, since we have more than one input feature, and we need to find out the slope value. We need a slope value for each input feature. For the square feet feature, the slope is this one. For the bedroom feature, the slope is this one. So you need to multiply bedrooms with this one, square feet into this one. Bedrooms is a column name. In that case, if you use this column name and if you multiply this one, what will happen? Each and every records number of bedrooms will get multiplied this one plus each and every record square feet value. Let's here 1500, right? 1500 into this one will get multiplied and then it will get added with this intercept. That is what your predicted value. But you don't have to complete the predicted value, everything it is already computed. Look here, the mean absolute value is 6000 and mean squared error is we are getting this big. Root mean squared is 7419. R squared value is 0.9880. Okay, R squared and adjusted R squared also we have seen it. Adjusted R squared is not coming out here, right? Okay, let me do one thing. Okay, adj R2, right? So ADG R2, this is what the adjusted R squared value. I just print it somewhere here. Sorry, here I should mention, okay, adjusted or 2. If I scroll down, yeah, adjust also 0.9921. Okay, if you want R squared also, you can mention it. Since it's a multiple linear regression, adjust R squared is the one will give you the correct picture, okay? 0.9921, which is closer to 1. But guys, remember very well, in the real world scenario, you will not get 0.99 and all, okay? It will be somewhat, 0.92, 0.93, you will get that one, okay? But usually we compute the R squared value on the test data only. This is my test data, predicted value of the test data, right? That is the one I supposed to use it. But we have very less number of records are there in the training data set. Sorry, in the test data set, I have used the training data set to itself to make a prediction. See, I trained the model using the training data set, and also I applied the trained model on the trained data itself to make a prediction, because less number of records I have it in this demo data, okay? And hence, so in the real world scenario, right, you need to apply this on the test data set, okay? Instead of y underscore train, y underscore test, y underscore train underscore pred, or y underscore pred, right? This is what it is, right? So you are supposed to pass the test data sets predicted value and test data sets the actual value. When you pass it, that is the one your test data sets predicted value, or the adjusted ask value. You need to compute it that way, okay? So they will ask you what is the training adjusted R squared value, what is the test adjusted R squared value. So in that case, you need to use one more line here, something like that, or or simply write, you can say R squared is also fine. So y underscore test here, or in our case, yeah, y underscore test. In my case, the predicted values, we stored it in a y underscore predicted value. This is the actual value of your test data set for the housing price. This is the predicted value of housing price. You need to buy the here, R2 underscore train. R squared value for the test data set is whatever you get it right, that is what you are tested. So in that case, you need to tell your manager what is the R squared value for the training data set, what is the R squared value for the test data set. And similarly, root mean squared error, right? So mean squared error, root mean squared error also you can, compute it. In this case, let me see what is the root mean squared error. Yeah, here, look here, correct. Here, I obtained the a mean absolute error and the root mean squared error for the training, sorry, test data only, okay? So this is how you need to do it, okay? And here, the actual value of the housing price from my test data set, and then the predicted value of my test data set. And for this, right, I'm use the mean absolute error. And again, there is a function called mean squared error. Even for this, you need to pass the actual and predicted, you need to pass it. And then finally, root mean square root, np dot square root of MSE. If you take there is a numpy, np stands for numpy package. You remember just above this, right? The top of this one, I use the import to the numpy package, numerical Python package. The alias for that one is np. In the numpy package, there is something called square root function is available. np dot square root MSE. If I do that, yeah, you're right. It will take the root mean squared or mean squared error. It take the square root on your mean squared error. That's all, guys. Okay. I printed the root mean squared error also. Okay. And you can see down here, root mean squared is 7419. So lesser. Okay. Now the question is, what am I going to understand with the root mean squared error 7419? What am I going to understand here? So this is the error. Your root mean squared, you are getting it, which means, right? Lesser the error, better the model accuracy. Lesser the error, better the model accuracy. Simple example, yes, here, look here, we'll go back here. So look here, look at this number. This is my actual value. The predicted value is 2.8. Very slight variation. Okay, 4 and 3.2. But little bit difference is there. 2 minus 3.6, right? Here what happened? If you subtract the predicted value from the actual, 2 minus 3 minus 1.6. Okay, minus 1.6 you will get, correct? Yeah. So in this case, what happened? Negative value. Sorry, what happened? Opposite, right? 3 minus 6 minus 2. minus 1.6, we got it. So 4 minus 4 is it supposed to be actual minus 4 is 0, right? Yeah, sorry, 0. There is some problem here. So 4.4 minus 5. Okay, so there is y minus 5. There is some mistake here. Okay. Okay, this is how, guys. Okay, you need to say either you can subtract, the predicted value from this one. These were actual value and predicted value. Yeah, right. So 3 minus 2.8, 4 minus 3.2 minus 3.6, 4 minus 4 is 0. And that means, right, in this case, both of them are same, actual and predicted. That means my model predicted accurately. Okay, and 5 minus 4.4. Okay, so in this case, there is a variation here. But if you subtract the predicted value from the actual value, the difference should be less, very less. Okay, so this is the error, right? The actual minus predicted is your error. Got it. So the error should be less. Okay, the lesser the error, the better accuracy. See, you are telling someone, right? The actual price is 3, but you predicted 2.8. Okay, in that case, what that person will say? Yeah, minor variation is there, right? The error is less. And you predicted, for example, so the actual price is 4, but you predicted, 2.2. The difference is too high. That means the error is very high. That means your accuracy is not good. Correct? So higher the error, lesser the accuracy. I just write it here. எப்படி திருப்பி போட்டாலும் நம்ம வந்து ஸ்டடியா இருக்கும். Like actual price is 4. Let's say your predicted prices, you used your machine learning model, you predicted it. The predicted price is 2.8. So the difference between these two are what? 2.2, right? The difference is the error is more. Let's say instead of 2.8, if it is going to be 3.8, the error is, what is the 0.2, right? Lesser the error, better the accuracy. But here the more the error, right? So more the error means the accuracy is less. You need to interpret that way also. Got it? So what is the rationale for R squared? How did we compute the R squared? We have used this formula, right? The predicted value minus the mean value squared divided by, this is for finding out the R squared value. So adjusted R squared, you need to use that formula 1 minus R squared into n minus 1 divided by n minus k minus 1. That is the formula we use it to compute the adjusted R squared. Like R squared, for R squared, we have R2 underscore function is available. For adjusted R squared, I have written a custom function, my own function. How to write a user defined function? You need to use something called def. This is the one. This is a reserved word followed by the def. If you specify your function name, you can specify your function name, and then these are the arguments. You can pass the arguments for this one. So what are the values you pass it? That one will get substituted here, and then it will return. What are the formula that you mentioned? That one will get returned. So what I did, I have called this function followed by the equal sign, adjusted R squared, and all the parameters value, whatever I want to pass it, right? R2 underscore train, and n underscore train, k underscore train. I'm going to pass these three parameters to this one. It will get substituted, and then it give me the adjusted ASCII. That one will get stored here. That is the one I printed it here. So this is a little bit of fast tracking way. So I know freshers are there. If you do not know user defined function, don't worry. Understand the big picture, and then we will have a separate session for Python. Meanwhile, I would suggest you to look at our Python videos. We'll share that one also in our course. Okay, I have a separate course for Python. That course also will include it. You can also start practices side by side. But this is a way that you can fast track it. Okay. So guys, remember that once you join a software company, don't expect they'll train you everything from the scratch unless you are a fresher. Okay, let's say campus recruiting. But once you join as a 1 year experience, 2 year experienced, what they do is, right, in case of any new training, they will put you for 5 days training crash course. They'll call someone from the external or internal, Experienced people, they will train you in 5 days. They'll say, data science training is over. And sixth day, they'll ask you to start work on the project, real-time project. Hence, you need to, learn it, scale up in a pretty fast manner. But anyhow, I will include the Python course there. But at this moment, you just understand the big picture. So for what we did, yeah, what we did, right? We just, fitted this, the model, as per the machine learning. We just aligned this with our machine learning model. We just, data collector and data, exploratory data analysis, we did it. And then what we did, we have trained the machine learning model, but we did not do any feature engineering here because oddly we have two features are there. We did not do any feature engineering. Feature engineering, I know if you want to add additional features, you can add it, but that is optional. It depends on the project. Some projects, by adding additional features, it may increase your model accuracy. See, sometimes what will happen when you train your machine learning model, your accuracy is going to be, let's 0.76, 0.78 only you will get it. But customer will be saying that no, I'm not happy with that. Why don't you increase the accuracy further? That's why I paid you guys. So why don't you, for let's you're working with Cognizant. Hey, Cognizant guys, right? I paid you guys to increase the model accuracy. Okay, not this one. I preferred, I expected. So what you can run by talking to the stakeholders, the company's stakeholders, or the different business department or relevant department people, right? Understand the domain very clearly and see if you can add any other input features which can explain your model further. So what is this R squared or adjusted R squared? R squared value, for example, here, my R squared value or adjusted R squared value comes around 0.992. That means, right, the proportion of variation explained by my input feature is 0.99 on the dependent variable. Okay, that means the remaining, right? If you subtract this one from 1, what value you will get it? Let's 0.0. Yeah, let's say, okay, I'll just do one thing. I'll just take this and I'm going to add a cell here. 1 minus this one. If I saw, sorry, 1 minus. See, the R squared value is supposed to be 1, right? But in real world, you cannot get 1. So hence, whatever the value or adjusted R scale value you get it, you subtract it from 1, right? So that is the 0.09. That means in the interview, if they ask you what is adjusted R squared, how do you interpret that? The proportion of variation explained by my R squared is, or adjusted R squared is 0.99, which means the remaining value, this is error, right? So the remaining thing is unexplained variation. The proportion of variation explained by model is this one. The unexplained variation is this one. Okay, 1 minus R squared value or adjusted R squared. That is the one will give you unexplained variation. Got it? So now that you understood what is error and how to compute the error and what is sum of squared error, what is the mean squared error, what is root mean squared error, you understood, and what is R squared and what just squared or just R squared, that you understood. And with that, you are ready to evaluate your model's accuracy. These are the metrics that you can use it to evaluate your model accuracy. Fine, you are done with that. Now you learned how to train a linear regression algorithm and how to apply the train the linear regression model on the unseen data to test the model performance using metrics like R squared, adjusted R squared, RMSE, MSE, mean absolute error. You are able to measure the model accuracy. Fine. Okay. Good question. One, she asked this question, Shufali. Okay. So, Satya, how can I, conclude, here, the big number is there, mean square is a very big number is there. So, is that correct? How can I say the error is less here or error is more? Very good question. So for that, right, we use the root mean squared error. You take the square root on mean squared error, you'll get 7418. That's a very good question. For example, right, if your management or the customer is not happy with the, let's assume that adjusted R square is 0.81 is there. Instead of 0.9921, 0.81 you got it. And the root mean square is 74318. And he says, right, he is not that happy. And he's asking you, is there any possibility that you can increase the accuracy? What you can do, right? One approach is you can try to add some additional features along with the existing feature. For that, you need to know the domain knowledge. After adding the additional features and test your RMSC. It's a இப்போ கரண்டா ரெண்டு ஃபீச்சர்ஸ் தான் யூஸ் பண்ணியிருக்கோம் இல்லையா? இன்னும் 2 ஃபீச்சர் ஆட் பண்ணிட்டு அப்புறமா RMSC செக் பண்ணி பாருங்க, அட்ஜஸ்ட் ஆர் ஸ்கொயர் செக் பண்ணி பாருங்க. So in that case, if you see an improvement in the adjusted R square, instead of 0.81, it got increased to 0.83 or 0.84 வந்துச்சு. Very good. So RMSC got reduced. The error got reduced. So 7,000 instead of 7,419, in the second iteration, you got 6,200. Shafal, you understood, right? That's how it's not one-time job. You need to it's an iterative job when it comes to real world scenario. Anyhow, I have some real world data is there. That is the one I'll give it to an assignment. Anyhow, I'll send you that in detail in the WhatsApp. Okay, you just take a look at that and start training a model. Okay. Okay, now the question is, how do I add feature, how do I do the feature engineering? For that, I just already I've shown you. For my data frame name is data, right? So my data file name is housing.csv. I loaded the data into a data frame called data. Okay, in this, if you want to add a new column, what you can do is inside the square bracket, you put the new column name, square feet per room. This is the new column I want to create it based on this logic. On the right side, what I did, I divided this square. This square feet is already there in my data set. Bedroom is also already available. If I divide the square feet by the bedroom, I will get square foot bedroom. So in this case, I was able to derive a new column. Based on the existing columns, I derived a new column. This is called feature engineering. Similarly, housing price is already there, square feet is there. If I divide the housing price by the square feet, I can derive the price per square feet. So I created a new column. If you want to create a new column, you put the new column inside the square bracket followed by the date, your data frame name. But make sure that new column name should be enclosed by single quote. Okay, on the right side, you can specify your business logic. This is your business logic. In this case, the square feet of a bedroom, if you divide this one, you will get square feet per bedroom, and then you will get price per square feet. So now what you do is, right, you got two additional columns. Previously, you were having only two features. Now you included two new features. So in total, now we have four features. Now what you do, right, after executing this cell, if you execute this one, you will find instead of two columns, two features, you will find four features. With that four features, you click on the next thing and then see what is the adjusted R squared value or what is the root mean squared error. After including the two new features, and if your adjusted R squared value increases further, and then if your RMSC value reduces it, then your model is doing. So you need to compare this is the baseline model, which means what are the features you gave me only two input feature. With that, I trained my model. I just got the accuracy metrics, right? I got the using the metrics I evaluated the model. Fine. Second iteration, what I'm doing is I'm going to add additional features based on some business logic. Okay, and then again I'm going to retrain my model, and then I'm going to evaluate my model based on these metrics. Okay, so with this new metrics, new additional features, are there any improvement in the adjusted R squared? Are there any reduction in the RMSC? See, error should be less. R squared is supposed to be more. Okay, that means the proportion of variation explained by my model, right? And the proportion of variation explained by my independent variable on my dependent variable is 0.99 something like that. It should explain more. Okay, and if it is not, listen, for example, 0.81 is there, your adjusted R squared. That means with the given input feature, The proportion of variation explained by your R squared is 0.81 only, but that means the remaining 19%, 19, the 19 percentage were unexplained by your model. To unexplained என்ன அர்த்தம்? Probably by adding additional features. இப்போ என்னன்னா just square feet வச்சு நம்ம with just having only one feature like square feet, if you train your model, do you think you can get the accurate housing price? So in that case, let's say your R squared value is 0.81. That means, right, only 0.81 or 81% the variation is explained by my R squared. That means there are chances that if you can add additional features, it can explain more the variation by adding features like age and location, age of the house, location of the house, number of parking lot. Maybe those features can improve your, or it can explain more variation, right? That means your error will be less and your accuracy will go high. Okay, so this is the term you need to know. Okay, lesser the error, higher the accuracy. Your objective is you need to reduce the error. To take any machine learning model, whether it's a Gen AI or machine learning or deep learning, when it comes to artificial intelligence, if you make any prediction, the error is supposed to be less. Your goal is trying to minimize the error. Okay, fine. You understood metrics, everything as of now. Next one is, wait, this topic is not over. We need to validate assumptions. When it comes to linear regression algorithm, apart from evaluating the model metrics, right, adjusted R squared, RMSE, there are some more things also you need to make sure that it is adhering to some assumption. There is something called assumptions. In the case of linear regression, 5 assumptions are there. So here, right, you need to 5 assumptions are something like multicollinearity. One is multicollinearity, linearity. First one is linearity. Second one is the multicollinearity, and the third one is autocorrelation. There should not be any autocorrelation. And fourth one is heteroscedasticity. Okay, if you find heteroscedasticity, there is something wrong. Homoscedasticity should be there. Okay, the fifth one is homoscedasticity and multicollinearity. Correct, multicollinearity. These are the things. Multicollinearity should not be there. In case of multicollinearity, you need to address it. We have seen it when we explored the heat map. We could see that square feet and bedroom were having some kind of collinearity. There is a correlation between the independent variable itself that is violating the linear regression assumption. What linear regression assumes is there is no multicollinearity. In case of multicollinearity, you need to, what is multicollinearity? Correlation between the independent variable itself. That is not acceptable. Okay, you need to address that one. Okay, so what I did here, right, there is something called stats models package. With sklearn, the disadvantage is, right, you cannot get a holistic picture about all the 5 assumptions. Okay, look here, I have plotted these charts. Okay, and it's a normality. You need to make sure that the result should be normal. Okay, and 5 assumptions are something like linearity. I will just go through on it quickly. It's already, little late. I mentioned 11:30 was the cutoff time, but anyhow, I'll just quickly walk through the assumption. These are the 5 assumptions you need to remember: linearity, independence of errors, normality of residuals, equal variance, and no multicollinearity. Okay, so what is linearity here? The relationship between the independent variable and the dependent variable is supposed to be linear. You remember we've used the scatter plot, correct? Scatter plot, you can see that, right? So, there is a positive correlation, negative correlation. At least, positive, negative correlation should be there. There should not be straight line, okay? The relationship between input, that you need to validate it. That is one of the assumptions. Second assumption, independence of errors. That means no autocorrelation. The residuals or the errors are independent of one another. Okay, you remember here I put, right, this one. Yeah. So here, the green color is my actual value. This is the predicted value because the prediction line, this is a line, right? All the predicted value lie on this line, and the distance between actual and predicted value is called your error. This is error 1, error 2, error 3, error 4, error 5. This error, this error should not correlate with this error. Similarly, this error should not correlate this error. There should not be any correlation between the errors. It should be independent. Okay, that for that we can use some statistical test using which we can validate it, or we can plot that residuals versus predicted in a chart, using which also we can interpret it. And there is a test called Durbin-Watson test, using which you can find out are these errors are independent, or are there any correlation between the error. So the first assumption is linearity. That's pretty simple, right? The independent input feature, each input feature should be linearly correlated with my output feature. When it comes to second assumption, independence of error, the error is supposed to be independent, and which means, right, how do I check that one? We can use the simple statistics called Durbin-Watson test. So to detect the autocorrelation, that I will show you how to do that. Okay, and next one is the next assumption is normality of residuals. What do you mean by normality of residuals? All the errors when you plot it, it should be approximately normally distributed. All the errors when you plot it should be approximately normally distributed. Okay. Not only the input and output feature should be linear. Even when you plot the errors, right, it should be like something like a linear kind of thing, normal. Okay. For that, we use something called QQ plot or histogram of residuals. Okay. That is the one will help us to identify or the residuals are normal. Next one is equal variance. Homoscale. The residuals supposed to be constant variance across all values. Okay. You can check it using residuals versus predicted plot. There is something like residuals versus predicted plot. And fifth one is no collinearity. Okay. All the independent variables should not be correlated with other independent variables. Okay. So for that, we can use something called VIF, variable inflation factor. There is a function called VIF where you can use VIF, using which you can find out are there any correlation between the independent variables. If the variable inflation factor values greater than 5 or 10, that means there is a multicollinearity. Okay, in case of multicollinearity, what can I do? Okay, a person has a disease. Identifying the disease is not sufficient. What is the next step? Next step is you need to address it. How do I address it? That we'll see it little later. Okay. So far we have seen 5 assumptions. I'll just quickly repeat. Linearity is something like, the relationship between the independent variable and dependent variable should be linear. Okay. And for that, we can use residuals versus predicted plot. I'll show you that. Next one is no autocorrelation. There should not be correlation between one error to another error. For that, you can use Durbin-Watson test. And third one is normality of residuals. We can use QQ plot to interpret, the residuals are normal or not. Okay. And next one is the equal variance, almost the residual is supposed to be, or the error is supposed to be constant. Okay, and then no multi-collinearity. So there should not be any collinearity between the independent variable or amongst the independent variables. How do I test that? For that, you can use something called VIF, variance inflation factor function, using which find out. And how do I interpret? If the variable inflation factor is more than 5, that means there is a variation in my model. So what I do, right, I just quickly go through the chart here. Look here, I plotted, all the things here. So there is a statistical package, for all the 5 assumptions, right? I just plotted it here. And the first one, residuals versus predicted. On the left one, what it tells, this is the one, checks for model has captured any pattern. In this case, the x-axis, we have the predicted values, y-axis, we have the residuals. Okay. Okay, in this case, the red dotted line, right, is at 0. In this case, the red dotted line is at 0. So that means you have well balanced, or well behaved model. Okay. Um, so here the values are randomly scattered here. Okay, since it is good. Okay, since we can say it is kind of good, and it is And even the linear, to check the linearity, the first assumption, right? You can use the scatter plot itself, just as part of just above this I plotted it, correct? So you can also use that one. And then the second chart, QQ plot, QQ plot of residual, the middle one, okay? This chart checks if the residuals um, or our model errors follow a normal distribution, okay? You can see that dotted value, right? It's almost close to the straight line, correct? It is not too far from the straight line. Hence, the errors are normally distributed, okay? And then the third one is the Durbin-Watson test. So in this case, in this bar, right, it helps us to check for autocorrelation, right? Which means our errors are depending on each other or not. Okay, so it's simply right. You have some like when you run this test, right? Look here, it says the value is 2. The ideal value is 2. Reference value is 2. Like blood report, right? Reference value is 2 here. So good. And if it is way below 2, way below 2, so it's somewhat closer to 2, right? This bar. Okay, that means the errors are not auto-correlated, right? This is how you can interpret this one. And the third one, the next one is your QQ plot of residuals. It's kind of normal. It is already we have seen it here. This is the one. So and next one is the multicollinearity. Look here, there is something called VAF, variable inflation factor function, that is available as part of your stats package, stats models. Simply import this package and then you just simply follow this one. And you can see that when you execute this, you can see that the constant, you can ignore it. That's the, your intercept. And square feet, it gives you 110. Bedrooms, it gives you 155. That means these values are above 5 or 10. If it is less than 10, then there is no collinearity, right? So, but here it is more than 10, hence there is a collinearity between the independent variables, hence it needs some treatment. That we will see it, how do we, address this one? Probably what you can do, since square feet and bedrooms are collinear, you can drop any one of the feature and keep only one feature and then check. Okay, when you check that, what will happen if your variance inflation factor is falling less than 10, then it is good. And if your accuracy is, you might see some kind of increase in your accuracy, reduction in the RMSE by addressing the multicollinear. So even if you have multicollinearity, your error will also be increase. That is also another reason for increase in error. Okay, you need to address that one also. And then yeah, the linearity is simply you can plot, you can rely on the scatter plot. Look here, we can see the scatter plot. Already we have plotted the scatter plot here. Look here in this case, right? See the size, square feet are those, and then the price is a linear, right? Positive correlation. Here also, if you draw a line, it will be straight line only, somewhat straight line. Only these two variables, right? The linearity is there, and the normality of residuals, we have seen it using QQ plot, and you can see, right? These dots are somewhat close to this red line. Ideally, this one supposed to be there here. It will not get exactly like that, right? Somewhat close, but it's not too far from this. It's kind of okay. It is meeting that assumption, normality of residuals. And then the next one is the residuals predicted, Durbin-Watson test, right? So yeah, Durbin-Watson test, you can see that. And it is true, this bar, tells it somewhat, it should be less than 2 or 2, okay? So if it is more than 2, then that means, there is some kind of autocorrelation. Variable inflation factor, with that we can find out the multicollinearity, right? So linearity, multicollinearity, and okay, homoscedasticity. There is something called homoscedasticity. Homoscedasticity is something like, I just finish up with this one. Don't worry, it's already late. You need to go to office. Look here, when you plot that error, right? For example, you are this square feet, okay, and then here you have predicted values. Okay, sorry, residuals, which means errors. As the square feet increases, the error is supposed to be something like this, right? For example, your square, the error is something like this, and it's something like this. It's good. It's good. Okay, that means homoscedasticity. If you find an error something like this, something like a funnel kind of shape, as the square feet increases, my error also increases. That means this is called heteroscedasticity. Okay, so heteroscedasticity. We need to investigate it further. How do I do that? How do I investigate that? We will see it later. So if you see the funnel kind of pattern, that means it is violating the assumption. Ideally, it is supposed, this is called homoscedasticity. Okay. See, only the terms are, little bit difficult. Otherwise, nothing here. Okay. See, what it says, right? If the square feet of the house is 1000, my predicted value is something like, 1010. That means the error is, less, right? But when my square feet is 2000, my error is very high. As the square feet, let's say predicted value is 2500. And the actual minus predicted is 500. The error is 500. So likewise, as the number of square feet increases, the error also not supposed to increase it. Okay, it should be random like this. Okay, if it is 1000, the actual value maybe right 1200. Okay, so yeah, the error is this, and for the 2000 square feet, the predicted housing price is something like let's two. Okay, you just think this is the price here. Okay, 2000 means 2000 10 only predicted. So for this the error is like this. For this the error is like this. Then it is fine. But as you increase the square feet, the error is also more. Then something wrong. That is called heteroscedasticity. It is not, it's not adhering to the assumption. It is violating the assumption. Okay, that one we can plot it and see it. By plotting and seeing it itself, we can find out. Instead of plotting and seeing it, we can use some test. Okay, statistical test, or you can plot this data and you can see it. This one we will see it in the next session. Okay, next session most likely we'll have it on this Wednesday, and weekdays only one session. Followed by that, every weekend we will have a session. Okay, and I will share you one assignment with the data set, same housing price, but you will have more number of input features. You give it a try. Okay, you take this script. So all you need to do just put your data file, whatever the file that I give it, right? That you can specify. That's all. You can execute this one. It will work everything. Okay, automatically it will work. Okay, but only thing is, yeah, here this one will work. And only thing is when it comes to the train and test split, yeah, here you need to drop the column, right? The target variable, you drop it. When you drop the, or basically we are hiding the hiding the target variable, which means all the input features will get stored here, and then you are explicitly specifying it, store only the housing price value in the variable y. Okay, and if you go to the train and test split, here you don't have to specify all the input features, right? And we simply specify x contains all the input features, y contains your target variable housing price, and then you are doing the train and test to split here. That's all. Okay, only thing is you need to specify it here. Anyhow, you just give it a try. Otherwise what we will do is, right, in class we will practice it. Most likely this Wednesday in class we both will build the model, and then we will see how it works. Okay, so that you will get a complete hands-on. Okay, any questions? Yes, we will upload the video. You can watch it, tomorrow. And then, meanwhile, I will share the assignment. Take your time, Monday, Tuesday, and Wednesday night, we will sit together. We will solve that problem, problem statement together, okay? So that you will learn it. You can also build the model, right? Fine. Since you don't have any questions, I'm going to wrap up the session. See you all on this upcoming Wednesday night, same time, okay?